Swayam Prabha. Digital India. Educated India.
Good afternoon. So, in today's lecture, we will cover a couple of review topics as they relate to acoustics engineering. So, essentially what I will be covering is a bunch of subjects and concepts which you may have gotten exposed to during your high school years, or even during your first and second or third year while you have been doing your undergraduate program in engineering. So, some of these system concepts we will be mapping directly later in the course, in the acoustics course. So, it will be fruitful to review some of these and also practice a little bit more before we actually start walking deeply into the area of acoustics. So, essentially I will be covering 4 key areas. One is that I will in a very brief try to explain what is a linear system, because we will be using a lot of linear principles in the area of acoustics. The second area which I will be covering again very briefly today is the area of complex variables, and then associated with that would be complex time signals, and then that from there we will move on to RLC circuits as we use them in electrical engineering, because later in the course we will find some of the tools and techniques we use in RLC circuits to be very fruitful and useful in area of acoustics. So, that is in a brief the overview of what we will try to accomplish today. So, we will start with linear systems, and we have often heard that this system is linear. System A is linear, system B is not linear. But specifically, whenever we use a term linear, there is a context behind it. So, suppose one says system A is linear, then that person should be, unless it is really clear, should be explicit in saying that this particular system is linear in variables A and B, because you can have a complex system and it could be linear in some variables and it could be nonlinear in some other variables. So, we will take an example. Suppose I have a relationship y equals ax plus b, or I have another relationship dy over dt equals c dx over dt plus k. So, in this case the system is linear between y and x. In this case the system is linear between dy over dt and dx over dt, and of course, if I integrate this, then I will find that the same equation is also linear in y and x. So, here we can say y and x are linearly related, and we can make a similar statement in context of this particular relation also. So, I will give you another example. So, I have a second derivative of y. So, second derivative of y in time, let us say it equals a constant c1 times second derivative of x in time plus another constant c2 del x over del t plus c3 x. So, again by inspecting this whole relation, because the power of y is 1 in this whole relation, power of x in the entire relation is 1. So you can say that this is a linear relation between x and y, because x and y are on the opposite sides of the equivalence sign, and the second thing is that both the power of x is 1 and power of y is 1. So even though you are having higher order differentials, the relationship can still be linear if the power of the variables are 1 and they are on opposite sides of the equivalence sign. So typically if you have a linear relationship between two variables, and when you try to plot variable A versus variable B, you will get a straight line. The straight line can pass through the origin, or it can cut the x axis, or it can get the y axis at a non-zero intercept. So that is another feature for a linear system, that if I have two variables and I am plotting these two variables against each other, everything else being same, then I will get a linear response. The third feature is that I can use superposition principle. Position principle. So in a linear system, I am able to use a superposition principle. What does that mean? Suppose I have a system and I have an input x1 and it yields an output y1, and then in another case I provide it an input x2 and it yields an output y2. Then if I provide an input x1 plus x2, then if it is a linear system, the output will be y1 plus y2. So this is again an important feature of a linear system, which later, as we go deeper into the area of acoustics, we will be using to understand the response of systems when they are receiving complex time signals. Suppose a system which is linear in nature, it is receiving a frequency input of x1 hertz at a certain amplitude level, and it gives me a certain output response, and then it is receiving another input at x2 hertz, which is different in frequency, and it gives me another response. Then if I try to sum up x1 plus x2, then the response on the response, that is the output, will be a summation of the individual outputs. So this comes in very handy, and we also use this idea in the context of transfer functions, which we will learn later today itself. The third feature of a linear system is that if it is having a particular input shape or a particular type of a signal, then the output signal in the steady state situation will be of a similar shape. Whatever is going in, the output is going to be of a similar shape, whatever is coming out. And this is very important to understand, because if we are sure that there is a linear system, and it does not matter whether it is acoustics related or any other thing, and if we know that if it's a linear system in nature, and if it's receiving only sinusoidal inputs, and in the output if I am seeing a stepped function or a non-sinusoidal output, then either my system is not linear, or my experiment is not correct, or there is something wrong in my understanding or analysis of the whole problem. So consider a spring mass system which also has a damper, and then the spring and the damper are now connected to a mass m. The stiffness of the spring is k, the damping constant is c, and I am exciting this entire system by f naught e j omega t. So my input in this case equals f naught e j omega t, then my output response. So suppose I am interested in knowing the displacement at this point, and suppose I call it x. So then the output response has, so the shape of the input function is defined by this term, ej omega t. So output response also has to be such that it is some constant times ej omega t plus a phase, because the phase, this component, is not going to alter the shape. All it will do is it will induce a difference in the timing at which the peaks of input and the peaks of output happen. So if phase is 0, then the peaks of input function and peaks of output will coincide. If the phase is not 0, then they may not necessarily coincide, but the shape of the function for input and output will remain same. Another feature of a linear system is that if I have small changes in the input, then the changes in the output response will be proportional to the magnitude of changes which are coming in. So if I have small changes coming in, the changes in the output will be small in a proportional sense, because there will be a proportionality factor. If I have large changes coming in the input function, then the changes in the output also will be accordingly larger. So we will do another example. So I have a beam equation E I del 4 W over del x 4, and where W is the displacement of a beam. So in a beam equation I have this term coming up, and this is related to the moment exerted in a beam. Now here M and W are linearly related. Now we know that I equals the thickness of the beam time cube of it times the width. So BT cube over 12 if it's a rectangular cross section. So this is I. So if I put this in, then I get E BT cube over 12 times fourth derivative of the deflection equals moment. So again M and W, this may appear very trivial, but it's important to note, because as we do a more detailed analysis, M and W are linearly related, but M and T are not linearly related. So that is all I wanted to capture about what is a linear system, so that once we start solving complex problem in the realm of acoustics and also start doing experiments, we at the back of our minds be sure that the system which we are dealing with, is it really linear or is it not so linear, so that we are cognizant of whether our answers or experimental observations are consistent with our assumptions or not. So the second thing I wanted to capture was complex variables. So we know from our high school mathematics and also first and second year of engineering mathematics that exponent of Ej theta is cosine of theta plus j sine theta, where j in this course is -1. Typically we use I as square root of -1, but in this course we are using j as square root of -1 because we are using I for other variables such as current. So if I represent this graphically, I have a real axis, I have an imaginary axis, I have a vector as radius r equals 1, and this angle is theta. So if I draw a normal here, this value which is along the real axis is cosine theta, and the vertical component is sine theta. So this is my function and this is its graphical representation. So understanding this picture, we can then generalize that if I have any complex variable of the form a, plus bj, I am able to represent it in such a form. How do we do that? So again, let's say there is a complex number a plus bj, and if I have to represent it graphically, then the length of the radius will be the magnitude of this variable. So magnitude is a square plus b square, the square root of this term. Similarly, the angle or the value of theta will be such that it is tan inverse of b over a. So this is my theta. So using such an approach, again I construct a circle. This is my real axis, imaginary axis, that's my radius, and the magnitude is a square plus b square, and that's the value of theta, and that is tan inverse b over a, and this is in radians. So if I have any number 3 plus 4j or whatever number I have, I should be able to fairly easily represent it in this graphical format. So we can use these complex numbers in a variety of ways. We can also use them to solve equations. So let's say that I have an equation x cube plus 1 equals 0, and if I want to solve for x, so my x cube equals minus 1. Okay. Now let's see how we can represent minus 1 in a graphical format. So minus 1 could be written as e j pi. We can also write minus 1 as e 3 j pi. We can also write the same thing as e 5 j pi, and so on and so forth. So my x is cube root of this thing, so is either it could be e j pi over 3, that could be one solution, or it could be e j pi, which corresponds to this value of minus 1, or it could be e 5 j pi over 3, and so on and so forth. So now let's plot them on the complex plane. So I draw a circle, that's my real axis, this is my imaginary axis. So my first solution was e j pi over 3. So pi over 3 is 60 degrees. So that is my first solution, x1. x1 equals e j pi over 3, and this angle is pi over 3. My second solution, x2 equals e j pi. So this is my x2. My third solution is x3 equals e 5 pi j over 3. So 5 pi j over 3 is here. So this whole angle, this angle is 5 pi over 3. So this is my x3, and all other solutions x4, because this will have infinite solutions, will be basically repetitions. So my x4 will be same as x1, x5 will be same as x2, x6 will be same as x3, and so on and so forth. So I have a graphical representation of 3 unique solutions for the equation x cube plus 1 equals 0. We will very quickly cover some very fundamental basic identities now about complex variables. So let's say z equals a plus bj. So I can express it as a real number d times e j theta, where theta, as we saw earlier, is tan inverse of b over a, and d is the magnitude a square plus b square, the whole thing square root. And then I have another number z star equals a minus bj. So I can express the same thing as E minus j theta. So Z star is complex conjugate of Z. This is our definition. So a complex conjugate of Z, which is A plus Bj, is A minus Bj. And a property of this is that Z times Z star equals D square, which is the magnitude square. Couple of other identities. If Z equals 1, then in complex plane I can write Z equals E j theta, where theta could be 0, 2 pi, 4 pi, and so on and so forth, or it could be minus pi, minus 3 pi, and so on and so forth. Similarly, if Z equals j, which is a unit length along the imaginary axis, then in complex plane Z could be represented as E j pi over 2.
So if theta is minus pi, then z is minus 1, sir. Because cos pi is minus 1, and also cos minus pi is minus 1.
Actually, you're right. So actually, it should have been
Only
yes. It should have been 0, 2 pi, 2, or an alternative solution could be Z equals minus
2 pi.
E j theta, where theta is
Yes.
this thing.
Yes.
So I have two sets of solutions. One is E equals plus E j theta, where theta equals 0, 2 pi, 4 pi, and so on and so forth. And the other one is Z equals minus j theta, where the associated theta values are minus pi, 3 pi, and so on and so forth. Okay? So going back, if Z equals j, then Z could be E j pi over 2, and then we can again, or it could be minus E j 3 pi over 2. So similarly, if Z equals 1 over j, then I can call it as E minus j pi over 2 equals minus j. So these complex variables can be used in a variety of ways. If I have additions of different phases, and if I use complex variables, I can very easily add the exponential term and then express the exponential terms in terms of cosines and sines, and I am able to manipulate complex additions and subtractions of vectors by using the idea of complex variables. So for instance, I know that cosine plus pi over 2 is minus sine theta, but if I have to use complex variables, it is basically real component of E j theta plus pi over 2 equals real component of E j theta times E j pi over 2 equals real component of cosine theta plus j sine theta, and then I now expand on E j pi over 2. So cosine of pi over 2 is 1 plus, no, cosine of pi over 2 is 0 plus j times sine of pi over 2 is 1. So I get real cosine theta times j minus sine theta equals minus sine theta. So I can prove some complex identities also using such an approach. This is again a simple illustration, but we will use some of these principles and notations for calculation, and that will make our life significantly easy. So we have talked about what is a linear system. We have very briefly captured about some basic things about complex variables. So now we will talk about complex time signals. Complex time signals. So it happens that quite often we develop differential equations in time and also or space. For instance, you have a spring mass damping system such as F equals mx double dot plus cx dot plus kx. and we have to solve it. And in such situations, this notion of complex time signals comes in very handy. So we will do that. Suppose you have F equals mx mass times acceleration plus damping times velocity plus stiffness times displacement. So a solution for this kind of an equation in a very general sense could be of form x bar est, where x bar and s both can be complex numbers. So again, a very general solution could be of this form x bar est, where x bar is a number and s is a number, but they need not be real numbers. And x bar is called complex amplitude. Also S is called complex frequency, and this can be decomposed further as sigma plus j omega, where sigma and omega are real. So sigma and omega are real numbers, but S itself could be a complex thing. So if I have this kind of a representation, my velocity will be real component of S x bar est. Basically what I have done is differentiated the displacement, and then I take its real component, that is my velocity, which I can physically measure. Also note that if I have to integrate this thing, so that gives me x bar over S est. So again, differentiation and integration becomes fairly simple process.
Here, assuming that x bar doesn't contain time t.
X bar is a constant. It can be imaginary, it can be purely real, but it does not have time embedded in it. Yes.
So
The time is in
So
t.
basically this, and that is because it's a linear system.
We have assumed the shape of, well, I mean, I am not using features of linear system to talk about this, but I have assumed that x bar est is a complex time signal. It could be anything. I am not even saying right now it's a solution of this thing. If there is a complex time signal of this shape, then this is by definition called complex amplitude x bar. S by definition we are calling complex frequency, which is equal to sigma plus j omega, and x bar is a number. It's not having time embedded in it. So, and then if I have to find velocity, I know complex displacement, so I just differentiate it and take its real component. This is my velocity. If I have to integrate x, all I have to do is divide that by s. So that's all I'm saying. So we'll do an example. So let's say my x bar equals 3 e j pi over 4, and s equals minus 2 plus 4 j. This is to black color. So my x t equals, the way we have defined, is real component of x bar e s t, right, equals real component of 3 e j pi over 4. So again, there is no time in it, in x bar itself, times e minus 2 plus 4 j times t. So the time is right now only in the exponential part. Just to reiterate, x bar and s are not functions of time themselves. So now I rearrange, so I get real component of 3 e minus 2t. So I am basically breaking up into real and imaginary component times e j pi over 4 plus 4t. Did I do the math right? Minus 2t j pi plus pi over 4 plus 4t. So which tells me, so this is real, so I can take it out, times, and then the real portion of this guy is cosine 5 over 4 plus 4t. This is my x. Okay. So we have broken it x into two components. One is an exponential component and then other one is an oscillatory component, and we are multiplying both of them based on mathematical manipulations which we did here. So now we will plot x as a function of time. So we will plot this function over time. So I am plotting x t here. This is my time axis, and so I get my plot something like this. And so on and so forth. And the envelope is defined something like this. So this is the envelope, which is a plot of 3e minus 2t, which we got from here. So this is defining the envelope. And the oscillating signal is the actual value of the function over a period of time. It just happens that because the phase difference here, there is a non-zero phase value which is pi over 4. So at t equals 0, this point is not touching the envelope. So based on what we did earlier, x bar equals 3 e j pi over 4, and this has two components. One component is 3, the other component is pi over 4. So this is like your envelope's upper limit. That is the maximum value the function can get. This is your phase. And then the complex frequency is minus 2 plus 4j. Again, it has a real component, minus 2, and this is rate of decay, and it's symptomatic of the damping characteristics of a system. And then you have 4, and that is essentially your angular velocity. So you have a complex amplitude which tells you the magnitude, which defines the magnitude also, and also the phase part of it. And then you have complex frequency, which helps you understand the damping characteristic of the oscillation or the signal, and also the angular velocity or the frequency. So that's all I wanted to talk about complex time signals, at least today, and we'll talk more about complex time signals as we move forward. So now we move on to the third big category, what we'll be talking about today, and that is about RLC circuits. So resistance, inductance and capacitance circuits. So we all know that the first electrical element very commonly used is a resistance. If I have current I and R, then voltage across the resistance is I times R. Similarly, if I have an inductor of value L and there is a current going through it I, then voltage is rate of change of current di over dt times L. And then finally, if I have a capacitance, I is the current going through the capacitance of value C, then the current and voltage are related such that current equals capacitance times rate of change of voltage. So these are the three basic elements in electrical circuits which we will be using a lot in acoustics. Then we have Kirchhoff's current law, which essentially says that if I have a node through which there is flow of current I1, I2, I3, then Kirchhoff's current law says summation of I1 plus I2 plus I3 equals 0. Another law developed by Kirchhoff's is called KVL, or Kirchhoff's voltage law. So I have a loop, a closed loop of electrical circuit. Let's say around this element I have a voltage of V1, here I have voltage of V2, and here I have, these are three elements A, B, C, and here I have a voltage difference of V3. Then Kirchhoff's voltage law says that if I go around a loop, then it's V1 plus V2 plus V3 equals 0. So we will be using these notions also in acoustic circuits. So that's why it's good to recapitulate those. So the other thing I wanted to talk about, so let's look at a circuit. So we will do a very simple example and use some of these electrical engineering elements and try to understand them a little better, and also recapitulate some of the concepts which we have learnt earlier. So let's say I have a circuit with a voltage source Vi, which generates current I flowing through a resistance R and also a capacitor of value C. So the question is that if I know Vi, which could be pulsating, then what is the voltage difference across the capacitor as a function of time? So we know that VR plus V naught equals Vi from Kirchhoff's voltage law, and we also know that VR equals IR, and we also know that I times I equals dV naught over dt plus times capacitance. So current and voltage across the capacitor are related by this thing. So if I synthesize all these relationships, what essentially I get is Vi equals RC dV naught over dt plus V naught, and what you have here is first order linear differential equation. So this equation, when we try to solve it, a very general solution will have two parts. One will be what we call a homogeneous function, and the other will be a particular response. So we will have a homogeneous response and we will have a particular response. And the homogeneous response will be highly transient in nature. So after a certain period of time it will decay. So for instance, if I have a system, if I have a glass and a moving mass hits it, initially the glass will shake, but after a certain time it will start moving steadily. So the initial response is called the transient part that dies over a period of time. In a lot of acoustic systems, we are more interested in steady state response. So we will focus a little bit more in this course on the steady state response of the system, and we will focus not that much on the transient response of the system, because a lot of physical devices, suppose you have an engine which is running, and once I start an engine, there is a perturbation in the system, and you have here one particular type of noise coming out from the system. But once the engine has started running, the sustained noise level is of a different, it may be of a different type. And in general, people are bothered that over a period of time, how does the engine sound, rather than what happens right at the point when you are starting an engine. So we will be focusing a little bit more on the steady state response of our acoustic systems. And that we can do in a fairly straightforward way if we use complex variables and also Laplace approaches. So for this particular function, let's say that Vi is real component of Vi est. This is known. Input. I know how a power generator is working, so I know this. So if I know this, and if the system is linear, then my output also has to have a similar shape. So I can assume that V naught is real component of a complex time signal V naught est. So now I take this relation and I plug it. So I put this relation and the relation for V naught in this entire equation. So what I get is V I est equals RC times d over dt of V naught est plus V naught est. And now I differentiate and do the math. So what I get is RCS V naught plus V naught est. So I get V naught equals Vi over 1 plus RCS, or V naught over Vi equals 1 over 1 plus SCR. So this will help me determine the steady state response of the system. The time component is embedded in this exponential term. I know Vi, so I can calculate V naught, and then I take the real component of V naught est and I figure out what is the actual physical voltage across the capacitance. So again we are seeing that the complex notation comes in very handy to solve some of these problems, especially if we are interested in solving steady state response of systems. So we had drawn this circuit Vi and V naught. So input was Vi and output which we were trying to find out is V naught, and we developed a ratio. V naught over Vi is this thing. This ratio is called transfer function. In a strict sense, here it just happens that V naught and Vi are the complex magnitudes of the actual voltages. In a very strict sense, the transfer function, which can be designated as Hs, is basically response over input. But it just happens that est in this thing goes away because it's a linear system. So transfer function, this is what we call a transfer function. And linear systems, the time component of it will always go away because it's a linear system, so they will cancel out. And the idea of transfer function works only in a linear framework. We don't use a whole lot of transfer functions in nonlinear systems because they depend on time, and then for each time instance you could have a different ratio. So then it becomes very complicated. So rather there you solve equations in time, in real time itself. So we'll write couple of transfer functions. So Hs equals if my Hs or transfer function is V over I, then for a resistance my transfer function is R, right? For an inductor my transfer function is, so this is again current going through the resistance and the voltage across the resistance, the ratio is R. For an inductor with value L, this number would be S times L. For a capacitor of value C, the transfer function would be 1 over SC. So again, it's handy to remember these ratios, these values. And what we will do in another example is that we will construct a circuit. So
Those transfer functions were for what, sir?
so the transfer function is in these three elements, the transfer function is basically the ratio of voltage across the element and the current going through the element, not through the whole circuit, current going through the element and voltage across the element. If I take the ratio of those, then I get these values.
They are the ratio of the complex complex voltage.
So transfer function can always be complex because they are ratios of complex entities. Remember, when we did this, V0 is complex and so is Vi is complex. Similarly, I can be complex. When I want to measure the actual current, then I take its real component. The phase is embedded in the imaginary part, but the ratios of V0 and Vi. So this is complex, this is lowercase, that is real. This is a real number. Similarly, V0 is complex, but lowercase is real when I take real component of V0 EST.
And what about S, sir?
S is again complex. It can be complex.
It can be.
As we saw in an earlier case, if you have vibrations and if they are dampening over a period of time, it can have a real component and an imaginary component. And if it's a pure vibration, if it is a pure non-dampening vibration, then it will be purely imaginary. So we will do an example and see how we use some of these transfer functions to simplify circuit analysis. So let's say I have a voltage source Vi and I have a resistance R and inductor L and a capacitor C, and I am interested in finding what is the actual voltage across capacitor. So one approach which we saw earlier was add these up, develop a differential equation and solve it. There is a faster approach. So the question is that what is V? So to do this, maybe I can be well placed if I can figure out what is V0 over Vi, which is complex representation of V0 and Vi. So how do we do that? If I know this ratio, that is the transfer function, then I can very easily multiply this times this, find V0 on the complex plane, take its real value, and that gives me V0. So a relatively straightforward way is that I transform this circuit in frequency space, which means that I replace R by its equivalent transfer function, which happens to be R. I replace SL by its, I replace L by SL and C by SC. So I am transforming this in frequency space or frequency domain. So Vi transforms into a complex entity, uppercase. R remains R. Inductor transforms to SL. And there is a mathematical proof, but we are just capturing whatever is the learning from electrical engineering here directly. And this capacitor gets transformed into SC. So now I compute the impedance of this circuit, and I don't have to worry about phase and everything, because the phases are embedded in these things themselves. So let's just first compute the impedance of this block. So impedance, let's call it is Z. So in that case, because SL and SC, these are in parallel, it is 1 over SL. We just assume that they behave like resistors, even though, because there is S embedded here. So 1 over SL plus impedance of a capacitor is this, and then I take inverse because they are in parallel, and what I get is 1 plus S square CL over SL, which is SL over, oh, I have to take inverse of this 1 plus S square CL. So I make another circuit. I have a resistance R, I have this impedance Z, where Z equals, we calculated SL over 1 plus S square CL. So what we have done is just replaced, and we are in frequency domain, and we are trying to find the voltage across this impedance Z. So now we can calculate V naught. So V naught is what? If my complex current is I, then it is basically Vi over R plus Z, right? That is my current, complex current I, and then I multiply that by Z. That will be the voltage, complex voltage across Z. So I do the math. So I have Vi over R plus SL over 1 plus S square CL, that is my complex current, times Z, SL over 1 plus S square CL. So if I do this entire math carefully, what I get, my final relation as V naught equals V naught over Vi is SL over S square CLR plus SL plus R. So I know now I can multiply this by Vi and take its real component, and I can figure out what is my actual voltage going to be. So again, you are using complex variables and also the idea of complex time signals, and what you are doing is you are converting circuits which are in time domain into frequency domain by making these transformations. You are replacing L by SL and capacitance by C, and then you are adding them up appropriately and then calculating complex current, complex voltage, and then mapping it back by taking their real components.
So even in the frequency domain, the Kirchhoff laws hold, sir?
It holds.
I mean, is that any special property, or it can be taken just?
See, the current will still has to hold something. Conservation laws have to work. Similarly, energy laws have to obey the same principles. So they still hold. If they don't hold, then you cannot do a circuit analysis. Then you need another system. So they have to hold. So we'll do one final example. So suppose I have some black box. Of some impedance. So the complex current is, let's say, I, and complex voltage is V. And let's say that the transfer function, which is a function of S, which is complex frequency, like in this case, complex function is a function of S. It depends on frequency. So this is equivalent to S square plus 2S plus 2 over S square plus S plus 1. And the question is that if my current signal real current I is something like this. It's a flat line. So it's like a step function at t equals 0. Before t equals 0 it is 0, okay. At t equals 0 it goes up and it becomes 1, and this is my time axis. So before t equals 0 it is 0, at t equals 0 it steps up, becomes 1 and remains constant throughout the thing. So if this is my current, what will my voltage look like, given that this is the transfer function? So in this context we should remember that this is a linear system, right? What does that mean? That if my steady state input, let's say I, is constant, then my steady state output, if output, the unknown is V, that will also remain constant, because it is a linear system. We are using that feature, bring it here. So I go to the complex domain and I say V over I equals S square plus 2S plus 2 over S square plus S plus 1. Now I know, so I expand this, I get S square V plus 2S V plus 2V equals S square I plus S I plus I. Now these terms relate to derivatives of current and voltage, second derivatives and first derivatives. So when everything is steady state, these terms can be, in a steady state situation they will be 0. Is that right? So 2V equals I. So if my current is 1, then voltage is 2. So transfer functions tell us a lot, and they are basically properties of the system. They do not change with excitation signals, input signals. They are properties of the system. For instance, in an electrical circuit, we saw that they are dependent on resistance, inductance and capacitance. And of course, there is a dependency on frequency. In that sense, they are dependent on the input, but they are a property of the system. So if I know my input, if I know my steady state input, I should be able to figure out my steady state output. So that's all I wanted to cover for today, and we will meet again, and we will again review a few more concepts in next 1 or 2 more lectures, and then after that we will move into the area of acoustics. Thank you very much.